This is a second video in a series of videos on Maxwell's equations and different representations. In the first video, we looked at taking the vector representation of Maxwell's equations, then assuming we have linear isotropic media, we derived the Euclidean spatial basis form of Maxwell's equations in geometric algebra. Next step, we're going to go from the Euclidean basis to a relativistic basis, the Dirac basis. We're going to derive the relativistic form, the space-time algebra form of Maxwell's equation. In between these two steps is some additional background on space-time algebra. I do have one video on that topic, and that is covering position 4 vectors, velocity 4 vectors, proper time, and proper momentum, and the expansion of those and to find the time-like and the space-like components of the two. The main point of those is of that in-between video, which I'll leave a link to, was to show that the representation of our spatial basis vectors in space-time algebra will actually be a bivector representation. We will represent each of E1, E2, E3 as a specific bivector, that is gamma 1, gamma wedged with gamma naught, gamma 2 wedged with gamma naught, or gamma 3 wedged with gamma naught. Each of those bivectors will be used to represent the Euclidean unit vectors for Euclidean spatial unit vectors. I'll review a little bit of that, but it won't go into the same detail as I did in the proper time, velocity, momentum video. So we got as far as writing Maxwell's equations in their Euclidean geometric algebra form with the electromagnetic field as E plus ICB, where E and B were vectors. So we have a vector plus I times a vector, which is a bivector. So it is a vector-bivector combination, multivector with grades 1 and 2 in the spatial basis. We also had a current and a differential operator. Our differential operator was the gradient plus 1 over c ddt. Like the current density that we had a multivector current density. Here we have a multivector space-time gradient, which acting on F was eta 0 minus j. Now, here is our charge density, and this is our current density. So we have a grade 0, 1 multivector, we have a grade 1, 2 multivector, and we have grade 0, 1 multivector, and it just happens to all work out. We saw that how it worked out, that this all represents Maxwell's equations in one bundled piece. We want to look to see now, how do we translate to the relativistic basis? Now, our relativistic basis, we make the identification that Ek is gamma k, gamma naught. And we're operating in a relativistic basis. We have gamma naught, gamma 1, gamma 2, gamma 3 components for our basis, where gamma naught is the time-like basis vector, and gamma 1, 2, 3 are the space-like basis vectors. And if we square our time-like basis vector, we get 1, and we square our if we square our time-like unit vector, we get 1, and if we square any of the space-like unit vectors, we get -1. I may have said that backwards initially. So, in particular, we can summarize this as gamma mu dotted with gamma nu is g mu nu. And g mu nu has a matrix representation of 1, -1, -1, -1, with zeros everywhere else off diagonal. It's possible to use the opposite sign for J mu nu, and that's not done in quantum field theory, but is done in some general relativity type contexts, maybe other things. But for space-time algebra, we use 1 minus 1 minus 1 minus 1. Not everybody likes that, but that is probably mostly a matter of comfort. So given the representation of our unit vectors, our spatial unit vectors as bivectors, and you could go and show that the space of all vectors that have this bivector basis is a vector space. There's no reason we can't use bivectors as a vector space or trivectors as a vector space if we had enough of them. For the STA, we should have 4 trivectors. 1, 6, 4, yeah, 4 trivectors. So you could use all those trivectors as a basis of a 4-dimensional vector space if you wanted. We're going to use this subset of the STA bivectors as a basis for our spatial space. If we enumerate all of the bivectors that we have gamma naught, gamma 1, gamma naught, gamma 2, gamma naught, gamma 3, gamma 1, 2, gamma, and I'm going to write 1, 2 as gamma 1 times gamma 2, gamma 1, 3, and gamma 2, 3. Those are all of these are the STA bivectors. So we're picking just these 3 as the bivectors for space, which is a little bit interesting because these have the last 3 are kind of logically spatial bivectors, but we want to treat the first 3 as our bivector basis for space-like quantities. Anyways, the reason that we want to do that, and I've described this in another video on proper time, proper velocity, momentum, and how to extract the time-like and space-like components of 4 vectors in space-time algebra. The reason that we are making that choice is that Ek squared is gamma k, gamma naught, gamma k, gamma naught, and we can pick any order to do this multiplication. And for this particular order, we can say that this is gamma k times minus gamma k, gamma naught. If we flip the order of any perpendicular vectors, then we change the sign, which is gamma naught. We can now drop our parens, and we have minus gamma k squared times gamma naught squared, which is minus 1 times plus 1, which is 1. So we've just shown that Ek, our bivector Ek, if we square it, we get positive 1, just like the spatial basis vectors in a Euclidean space. So now that we have a representation for all of our space-like quantities, we have spatial gradient, we have the spatial current density, we have spatial electric field, and we have a spatial magnetic field variable. Each of those we want to now represent as bivectors in this form. Ek is gamma k, gamma naught. So let's look at the current term to start with. So we have eta c rho minus j. Now, that is, let me write our current density as jk gamma k. I'm using a small j here because I want to use big J for something else shortly. So if we have c rho minus jk gamma k, gamma k gamma naught, because I was saying that j is jk times ek. So that is where the bivector comes into the picture. So gamma k, gamma naught. We've got a scalar now, and we have a bivector. And if we multiply this whole expression through by gamma naught, we're going to end up with gamma naught over here, and we're going to end up with plus or minus gamma k on this side. So let us see what that does to our current. Our multivector current is going to become a 4-vector instead. So that is going to be eta times gamma naught c rho minus jk gamma naught gamma k gamma naught. This is not a trivector, gamma k gamma naught. Instead, it's a vector that's proportional to gamma k because the common factors of gamma naughts are going to cancel out. So let's do a side computation. We have gamma naught, gamma k, gamma naught. That's minus, flipping the order of any pair of these. That'll be minus gamma k, gamma naught times gamma naught, which is minus gamma k times gamma naught squared. Gamma naught squared is 1. So we have minus gamma k. We are left with eta c rho gamma naught, and minus minus is plus, so we now have plus jk gamma k. What do you know? We have something that looks a whole lot like how we would represent any 4-vector, provided all we have to do is we need to make the identification. J naught is eta c rho, and jk for any k equals 1, 2, 3 is eta jk. So this is really saying that it's eta times j dot ek. So that's what I've my small jk is vector j dotted with ek. If we make this identification, now we have gamma naught c rho minus j is j mu gamma mu. We'll write that as j. Now, if we multiply one side of our equation by gamma naught, we have to multiply the other side of our equation by gamma naught. So let's write out Maxwell's equations now. So Maxwell's equations are going to be gamma naught grad plus 1 over c ddt f plus gamma naught c rho minus j. And we've just found that this is our 4-vector j. What is this beastie? Let's compute that. So we have gamma naught times gamma k gamma naught d dxk plus 1 over c dt. And we're going to write the customary form of x naught equals ct. So now that is, we're left with gamma k gamma naught gamma k, and we just computed that, which is minus gamma k. So we have minus gamma k ddx k plus dx naught. Now in relativity, we typically write all of our 4 vectors with upper indices. So really, if we have a 4-vector x, that's going to be x mu gamma mu. We can also write that as x mu gamma mu, where gamma mu dotted with gamma nu is delta mu nu. This is our reciprocal frame. I'll write that out, I don't have enough space. So gamma upper mu is one of our reciprocal frame basis vectors, and really reciprocal coming from inverse. So let's specifically look at this so gamma k, if we have minus gamma k, that is in fact 1 over gamma k. So that is 1 over gamma k dd xk. And I dropped the gamma naught here, but gamma naught was 1 over gamma naught. So this is 1 over gamma naught ddx naught. This is a much nicer quantity in terms of relativistic indices, because now we have mixed indices, lower, upper, everything matches. We use that as a check to make sure we're doing things right. But we don't normally write our gradients with vectors in the denominator. We want to write those as vectors in the numerator. And so what we do is we define dk as ddxk, but we give that a lower index quantity, and now our space-time gradient is left to be, so 1 over gamma k is gamma up k, and we have gamma lower, or partial lower, and 1 over gamma 0 is gamma up 0, and I don't know if there's a better way to say that. So now we have something that looks like a 4-vector with matching indices. This is a 4-vector with respect to the reciprocal frame, as opposed to the 4-vector with respect to the standard basis. And the reason for that is that our indices are in the denominator, so logically our basis vectors ought to have been in the denominator as well. So we use the reciprocal form of these basis vectors and then write things as lower index quantities. And there's names for lower and upper indices. I think they're covariant and contravariant, but I can never remember them. And in geometric algebra, it doesn't matter because we always match our indices. So we write this as gamma mu d mu. That is what we call the space-time gradient, and we denote that with nabla with no arrow. So this is not equal to the nabla that we would write in boldface in text or with an arrow anywhere else. So our nabla space-time gradient is this, where dk is the partial with respect to the kth, and d0 is partial, so we have d0 as dx0. So really we have d mu as dx mu. Here's our definition for our partial, and here's our definition for our space-time gradient. So with that definition, we now have grad f equals j. It's deceptively simple. We do need to talk about what f is, because f had a representation in the spatial basis, whereas here we have a 4-vector, and here we have a 4-vector. Here we have something. We need to know what the representation of the something is in the space-time algebra. So let's look at that next. So our spatial representation of f was our vector E plus ICB. So in the spatial basis, we have a vector and we have a bivector. because anytime we multiply a vector times a pseudoscalar, we get a bivector. What about an STA? So in STA, let's start with saying what's I. So our spatial representation, the three-dimensional pseudoscalar, was E1 times E2 times E3. Now we're representing each of these as bivectors. So that's gamma 1, gamma naught, times gamma 2, gamma naught, times gamma 3, gamma naught. And you can, as I've mentioned, we can choose to reorder any of these multiplications provided we toggle the signs appropriately. So if we do that, we can say flip this, gamma, so let's not flip that one, let's leave that one as it was. Let's flip the next one, gamma 1, gamma naught, times minus gamma naught, gamma 2, times gamma 3, gamma naught. Now gamma naught is 1, so we're left with minus gamma 1, gamma 2, gamma 3, gamma naught. And if we permute gamma naught so that it's at the beginning, where it looks like it belongs in the, for prettiness, but then, so the gamma naught to here, change the sign once. Here will be, well, so minus, plus, minus. So we're now left with plus gamma naught, gamma 1, gamma 2, gamma 3. What do you know? The pseudoscalar, the spatial pseudoscalar, is also the same as the pseudoscalar for the STA. This is our STA pseudoscalar. So now we have a representation of I in the space-time algebra. If that didn't happen to be the same thing, or if we chose a different sign convention for our space-time algebra pseudoscalar, then we would have to introduce a different symbol. But we won't actually need that because it's going to fall out. It was here in our electromagnetic field. We had an I. We're not going to end up with an I. We're going to end up with a space-time algebra bivector instead. We would have to see that. So we know what I is. Let's look at E. So E is EK, gamma K, gamma naught, where the sum over all of the K's, so K equals 1, 2, 3. So that is a bivector. What is our magnetic field contribution? I've already said it's a bivector, but let's see why that's the case. So we have gamma naught, gamma 1, gamma 2, gamma 3 times C, BK, gamma K, gamma naught. So that's ICB. Now, let's commute our gamma naught all the way to the beginning to wipe out this gamma naught. So if we do that, flip sign, minus, plus, minus, plus. With plus gamma naught squared, which is 1, times gamma 1, times gamma 2, times gamma 3, times gamma K, all times C, times BK. Now, for K equals 3, our gamma 3 will be obliterated, and we're going to left with a minus sign. For K equals 2, we can commute once, which gives us a minus. And that will, maybe I should just write these out. So if I expand out the sum, we have C minus C, gamma 1, gamma 2, and I'll use this. I'll say gamma mu nu if mu is not equal to nu equals gamma mu. So they're all shorthand. So I'm going to write gamma, or actually I will say that gamma mu nu equals gamma mu wedged with gamma mu. So that's what I'm going to mean by the shorthand. So we have gamma 1, 2 times B3, and we have plus C times gamma 1, 3, B2, and if K equals 1, minus plus. But then gamma 1 squared is minus, so we end up with a minus. So we have minus C gamma 2, 3, B1. We can tidy this up slightly as minus C times gamma 1, 2, B3 plus gamma 3, 1, B2 plus gamma 2, 3, B1. And I say that this is tidied up because every term here is an even permutation of 1, 2, 3. So now we have F is EK gamma K gamma naught minus C gamma 1, 2, B3 plus gamma 3, 1, B2 plus gamma 2, 3, B1. So we have bivector, 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 bivector. Our electromagnetic field in spacetime algebra is a bivector, and in fact has one of each, has a coordinate for each bivector. So in each case, we have gamma 1, 2, and we have gamma 2, 1 as bivectors that we can write in spacetime algebra, but they're equal to each other up to a sign. So we only end up one component per each of gamma 1, 2. So if we were to write F as, let's say, G mu gamma mu, oops, not mu, but here's a general bivector. In spacetime algebra, this particular, and we maybe include a factor of half here, since we're double counting overall mu nu. So we could go and map, actually I won't use G, I'll use the standard symbol because we would call this F. So we have a F mu nu for each gamma mu wedged with gamma mu, and provided here we need F mu nu equals F mu mu and F mu nu equals 0. But we actually need F mu mu equals 0 because that will be killed by the wedge product anyways, but it's convenient and conventional to write F mu nu as an anti-symmetric tensor with 0 trace. So that would be, this is our representation of F. So we write F now. That was a messy bounding box. So let's now just summarize what Maxwell's equations are. So we have grad F equals J grad was gamma mu, d mu, and d mu is d dx mu. F is half of all the possible. The F is a general bivector in the spacetime algebra. We don't know what it is. We have to solve for it. And we know that it's related to electromagnetic fields in this very specific way. So here is how F is related to the electromagnetic fields. We'll return to this in just a sec to understand it. And we have J as J is J mu, gamma mu, a 4 vector where J0 was eta C rho and Jk was eta J dot Ek. So that's, even though Maxwell's equation is one little line, it really means all of this. So it's compact, but it takes a lot of work to unpack it and see what it really means. The other thing we want to do is we want to understand when we have F here as an unknown bivector, how do we relate that back to our electric and magnetic fields? And if we go up, we can see here that because the electric field always has a gamma naught component, and the magnetic field, the ICB component, never has a gamma naught component, we can dot and wedge with gamma naught. We can take projections and rejections with respect to gamma naught to find the electric and magnetic field components. So we do that, we get that F. So F, if we project and reject with respect to gamma naught, will be F. Let me back up slightly. So let's say F equals F times gamma naught, gamma naught. And because gamma naught squared equals 1. We do that. Now we can expand out F dotted with gamma naught times gamma naught. So F gamma naught, if we pick this order to expand the products, is F dot gamma naught plus F wedged with gamma naught, and then we'll have multiplied by gamma naught. So F dotted with gamma naught plus F wedged with gamma naught all times gamma naught. This is electric field component, and this is the dual magnetic field component. So we can write our electric field is F dot gamma naught, and remember that if we take a bivector, let's say B is a bivector, and we take a vector, and we take the dot product of the two, then BA is 1/2 of BA minus AB. It's the opposite sign as the vector dot product with itself. And B wedged A is 1/2 of BA plus AB. It's a symmetric product of the two. So we use that, then we get 1/2 of F gamma naught minus gamma naught F gamma naught. which is half of f minus gamma naught f gamma naught. Similarly, if we take our magnetic field, and really, if we take ICB, then that is going to be f wedged gamma naught all times gamma naught, which is 1/2 of f gamma naught plus gamma naught f all times gamma naught. And I've hit the end of my page here. I can't go up anymore. So that is 1/2 of f plus gamma naught f gamma naught. Let me just make a new page and write that out in Scratch. So we found that our electric field component, in terms of the bivector f to be solved for in Maxwell's equations, is 1/2 of f minus the reflection of f in the gamma naught over gamma naught. So we reflect about the time-like axis and subtract off that reflection, we get the electric field. And if we have ICB, that is 1/2 of our electromagnetic field plus its reflection along the time-like axis. So this gives us a way of finding our, if we have our original electric and magnetic fields, we want to be able to extract those from our Faraday bivector, and the way to do that we've discovered is like so. So this, you can also write these in terms of f mu nus if you like, and we'll do that later when we get to tensor algebra, but won't bother doing that now. I'll just finish rewriting. So there's a summary of everything we found. So we found that grad f is j, and grad is gamma mu d mu, and d mu is dx mu, and f equals some bivector to be determined, and j is our source term, which was gamma 0 I'll just write it. J was, gamma 0 C rho minus J eta, which we are calling J mu gamma mu. That is a summary. Here is the space-time algebra form of Maxwell's equations in their full glory, which has this deceptively compact representation. But when we want to unpack what that is, this is what we mean. So that is it for space-time algebra. In the next video, we'll show how to take this representation and derive the full tensor algebra representation.